Building a complex software system from scratch is an exercise in managing change. When requirements shift, the system has to adapt. But when solving problems purely from first principles, engineers often default to writing tightly coupled code. Every component relies explicitly on the internal details of every other component. The result is a monolithic architecture. It might work perfectly on day one, but the moment a major requirement changes, the entire structure breaks unpredictably. To prevent this brittleness, expert architects rely on design patterns. These are recurring structural solutions that isolate specific axes of change, protecting the rest of the codebase. This methodology is built on two foundational axioms of reusable object-oriented design. The first, program to an interface, not an implementation. The second, favor object composition over class inheritance. To see how these rules operate in practice, we are going to architect a WYSIWYG document editor named Lexi. Along the way, we will encounter and solve 5 specific engineering bottlenecks. By applying these design axioms to Lexi, we elevate our focus from simply writing executable lines of code to engineering architectures capable of surviving inevitable system evolution. Lexi's first constraint lies in its document representation. The system must render a document where a single text character and a massively complex embedded diagram are treated exactly the same way. If we write separate, hard-coded conditional logic to handle text strings and graphical shapes differently, our rendering loop quickly becomes unscalable. Every new type of element would require rewriting the core loop. We define an abstract base class called glyph with standard operations. Primitive elements like characters inherit this interface, executing specific rendering code. Structural containers like rows also inherit this exact same glyph interface while holding lists of other glyphs. At runtime, a structural row does not actually render pixels. It merely iterates through its internal list of children and delegates the draw command down to them. This is the composite pattern. It allows the client application to treat individual objects and complex structural aggregations completely uniformly, eliminating conditional type checking. With the document structure in place, we hit our second bottleneck. Lexi must take these unstructured sequential glyphs and format them into distinct lines and columns. Line-breaking algorithms vary wildly. Use a fast, greedy algorithm or a complex text algorithm. Embedding complex formatting logic directly within the document's physical structure violates encapsulation. It forces the document to carry the weight of every layout calculation. We abstract the formatting algorithm into an independent class hierarchy. Document data sits in a composition block on the left. A distinct compositor object hierarchy is built on the right. The document delegates layout calculations to whichever algorithm is plugged in. This delegation allows developers to swap layout behaviors at runtime without touching a single line of the document's structural code. The strategy pattern demonstrates that encapsulating algorithms as interchangeable objects allows behavior to vary completely independently from the context that uses it. Our third problem involves UI embellishment. Lexi's core text view requires additional visual features, like drop shadow borders and scroll bars. The novice approach is to use standard compile-time class inheritance to add these new features directly to the text view class. This triggers an explosion of rigid subclasses, one for borders, one for scrolling, and another for both. The alternative is transparent enclosure. Instead of building larger classes, we introduce a single monoglyph object that visually wraps around the core node. The mechanics of transparent enclosure dictate that the embellishment object perfectly mirrors the interface of the object it encloses. To the rest of the application, the wrapper looks exactly like the original document. When a border decorator receives a draw request, it renders its specific UI geometry first, then blindly forwards the original request to the enclosed text. This is the decorator pattern. It allows for dynamic behavioral extension at runtime, bypassing the rigid limitations and bloat of static class hierarchies. Next, we introduce a portability constraint. Lexi must seamlessly adapt to fundamentally different operating system look and feel standards, like Motif versus Mac interfaces. If an engineer writes explicit constructor calls, asking the system to build a specific Motif scroll bar, the application is permanently locked to a single operating system aesthetic. Porting the software requires rewriting every single instantiation. This diagram shows how we abstract the actual creation of objects away from the core application logic. We introduce a GUI factory block that routes requests dynamically, outputting generic UI widgets. At initialization, Lexi is injected with a single concrete factory representing the current OS. From that point on, the application never asks for a specific widget by name. It just asks the factory for a standard button. The abstract factory pattern secures cross-platform portability. By isolating all OS-specific instantiation to a single interchangeable boundary, it ensures the core system only requests interfaces. This leads to a deeper operating system constraint. The high-level window logic that Lexi requires evolves at a completely different rate than the low-level rendering APIs provided by any given OS. Attempting to merge these two timelines into a single class hierarchy creates massive, unmaintainable bloat. You end up patching the core application continuously just to keep up with vendor updates. We solve this by splitting the problem into two parallel class hierarchies, shown here as window and window imp. They are linked strictly by a single horizontal object composition arrow. The high-level application window formulates the logical behavior, like resizing or minimizing, but delegates the exact pixel rendering across the bridge to the specific OS implementation. The bridge pattern prevents system lock-in by decoupling an abstraction from its implementation. Both systems can scale, evolve, and be replaced entirely independently. This master architectural map shows the finalized Lexi system. Notice how all the distinct engineering bottlenecks were resolved through delegation rather than hard coding. Just as important is what is explicitly missing from this architecture. There are no massive monolithic classes and no deep inheritance trees. In expert systems, compile-time inheritance is almost entirely replaced by runtime object composition. Strictly adhering to abstract interfaces acts as the supreme contract of the system, forever decoupling the what from the how. These patterns provide the structural rigor needed to satisfy our design axioms, ensuring that the interface remains distinct from its specific execution. Using these architectural patterns moves development beyond the writing of immediate instructions toward the creation of systems that remain stable under the pressure of changing requirements.